Greetings, cultivators worldwide. Jordan River here, back with more GrowCast, like a breath of fresh air. Today we got Nick from Rooted Leaf back on the line. We've got a mind-blowing episode about the oxygen evolution complex. I know you're going to love it. Check out growcast.com. Come and join membership where we hang out with Nick all the time. It's all waiting for you at growcast.com. Let's get to it. Thank you for listening and enjoy the show. Hello, podcast listeners. You are now listening to GrowCast. I'm your host, Jordan River, and I want to thank you for tuning in again today. Before we get started, real quick, growcast.com is where you can find all the stuff, the membership, the seeds, the classes, and all the episodes of this awesome show. We're also on video now, so check us out at growcast.com or find us on YouTube. Today, we've got a fan favorite back on the line. We're jumping right into it. You know him, you love him. Nick from Rooted Leaf is back once again. What's up, Nick? How are you doing, man?
Hey, Jordan, I'm doing pretty well. How are you?
Doing excellent, my friend. I can't tell you how many times I run into members. They say, I love the show, run into listeners at an event. I listen all the time. That guy, Nick, I listen to those episodes 2, 3, 4 times over just so I can understand what he's saying and just so that I can grasp these high-level concepts. I hear that all the time, Nick. So thank you, man, for coming back on the show for another deep dive.
Yeah, absolutely. And I appreciate all the feedback. You know, it's difficult sometimes to make the presentations in a way where people can listen to them multiple times and continue to learn new stuff without making it seem like I'm just trying to talk over everybody's head. So I really appreciate the people that have listened multiple times. I'm trying to structure the content in a way that makes it possible to listen to several times without getting bored. So it's definitely good to hear that feedback because it is my intent. And as we continue to dive into some of these more complex topics, we'll try to take that same approach, knowing that, at the end of the day, some of the stuff's a lot more complex than the stuff that we've talked about in the past. So there's going to have to be this quantum leap forward, if you will.
Oh, man. You do a great job of breaking it down, man. And you really are the advanced cultivation science guy. So we're getting into it today. Of course, before we get started, rootedleaf.com, code 20% off. Code GrowCast gets you 20% off at rootedleaf.com. If you're not completely satisfied with your nutrients, check them out. And we're continuing our deep dive series with Nick here. We talked about soil fertilizer elements first, and we went over all of those. You can find all of those in a nice playlist on our YouTube. Check them all out if this is your first time listening to Nick. And then we've branched off into some other stuff. You know what I mean? We start talking about things like pH and EH and these more complex topics. Today, we're bringing it back around, talking about oxygen again. I'm excited to speak to you, Nick, about a recap on Redux recap. Excited to talk to you about oxygen and what it does in our grow. And then this idea of OEC, the oxygen evolution complex. Very excited for another acronym, my friend. We love acronyms around here. And so let's dive right in, man. No reason to waste any time. Let's do a little recap on what we've talked about during these deep dives so far when it comes to redox and when it comes to oxygen.
Yeah. Redox chemistry is basically just reduction in oxygen chemistry. What it refers to is a transfer of electrons and how electrons basically get moved around and how they get stored. So the initial point of redox chemistry happens to be photosynthesis. So when the energy from the sun comes into the plants, that initiates this electron transport thing through kind of a complex series of events that happens depending on the specific wavelength that comes in. But everybody should be familiar with the 450 nanometers or the 680 nanometers that are in LED lights and maybe the full spectrum lights of a metal halide and a high pressure sodium. You know, you have those different color signatures because they're different bands that are being produced. And so, the idea basically is that this light energy comes in and it initiates this process of electron transport. Well, it's not enough to just transport the electrons because otherwise they would just keep moving forward, in perpetuity, and that doesn't do the plants any good. So really what they're trying to do is figure out, well, how do I turn that into useful work, or how do I turn that into a stable form so that I can access this energy for use at a later point in time? And this is how plants start to build up reduction power, so to speak. They build up the electron energy within the bonds of certain molecules. And depending on where we're looking at with like chloroplasts, for instance, or with mitochondria, we may have different sinks for the reduction power and where it ultimately flows. So in the chloroplasts, for example, this chart's a little bit different because what we're doing is we're looking, we see the photosynthetic electron transport system, but really what we're doing in the chloroplast is looking at oxidative stressors, reactive oxygen species that are produced naturally as a result of photosynthesis. And there's a very good reason why naturally reactive oxygen species are produced. I think a lot of times when people talk about reactive oxygen species, the context is always like this is a bad thing that we need to try to avoid. That's why we want to try to talk about antioxidants as being these good things. They prevent the oxidative stress. Well, it's also very true that on the back end, reactive oxygen species are generated as a natural byproduct of photosynthesis, and they actually do serve a role. That role is one that is a signaling based role. In other words, the specific kind of reactive oxygen species that's generated itself can be a form of a message or a signal for plants. And so, in a lot of ways, the generation of reactive oxygen species kind of forms like a logic loop, like you would find in a piece of hardware on on a computer circuit or something like that. It's like an actual loop that's formed as a result of this voltage or these electrons being shuffled through various metabolic processes. Now, to get a little bit more granular and a little bit more specific, the exact flavors of your reactive oxygen species can trigger different downstream effects. I'll give you one example. Carotenoids are those orange pigments. They are used by plants to help absorb excess photoexcitation energy. So, like when the light energy is too intense and the plants can't quite capture all of it, sometimes you have too much voltage going through the plants and they can actually physically burn as a result of that. So, plants have these safeguards called carotenoids built in. And as it turns out, when the carotenoids themselves absorb the energy, they can dissipate that energy. And that's the intended function. But at a certain point, the stress becomes too high even for the carotenoids, and they'll start to break down too. So you have this breakdown product of a carotenoid that actually ends up being a signaling molecule. It's called abscisic acid, and it's a hormone that downregulates photosynthesis. So the idea is there's this feedback loop. If the oxidative stress is too high, it starts to shatter molecules apart that are produced specifically to be broken apart. This is the intended purpose of why plants produce them. And once they get broken apart, it signals something to the plant. The plant knows that if there's a high concentration of this carotenoid that's been oxidized and broken down and turned into abscisic acid, that the process of photosynthesis actually starts to get downregulated. It's that feedback loop mechanism in place.
Jeez. It's like a GFCI breaker inside of the plant.
Yeah, exactly. It's what it is. There's also, in addition to the feedback loops, there's also what's called feed forward loops as well, or feed forward systems. So the plant is trying to set the stage before anything actually happens, so that it can properly tie things together. Because you have to think about from the plant's perspective, the photon energy is coming in at the speed of light, but the water molecules aren't coming up to the plant at the speed of light, and the rate at which the oxygen evolution complex can effectively, we'll call it splitting, but I'm going to make the argument here in this episode that it's really depressurization and not the splitting of water that happens. But when the oxygen evolution complex depressurizes water molecules, that doesn't happen at the speed of light either, right? So you have these things happening at different rates that the plant's like, all right, I need to coordinate all of this and have it happen all at once. Because the Calvin cycle, which fixes CO2, requires ATP, and that doesn't move at the speed of light. It requires NADPH, which is the one of the compounds that stores electron energy in chloroplasts, and it also requires CO2. Oh, did I say CO2?
You didn't, but that makes perfect sense.
Yeah.
So the light is the thing that needs to be regulated.
Yeah, there's a little bit of it's almost like the plants are trying to decelerate, right? They're trying to act like quantum scale particle decelerators to really just slow down the energy of the photons and store them in a useful way. And the water itself would be the deceleration matrix. We'll kind of get into the structured water, but on the particle deceleration side, you could think about it branching off into two different forks. One is like, okay, the photons interact with electrons. We know this from the electron transport chain, and we also know that photons have some I won't say direct interaction with protons, but I'm going to say that the interaction that photons have with electrons automatically generates some activity with protons. So there's a fork basically. When I say plants are quantum scale particle decelerators, really the fork addresses two things: is how does that concept relate to electrons, and then the other one is how does that concept relate to protons? Because this is the basis of acid-base chemistry. This is the basis of your redox chemistry. So like plants are trying to do this charge separation thing with electrons and with protons. And then they're also trying to do a charge recombination thing to make sure that they maintain a balance, a charge balance.
Right.
Yeah,
Right.
yeah.
Okay,
So
so I want to dig in on so much of what you just said, but let's focus in on the splitting of water because this is another thing that you've talked about in previous episodes. Real applicable stuff. When you talk about terpenes and cannabinoids being hydrocarbons, you talk about where that carbon comes from, and you talk about where that hydrogen comes from, and you talk about the splitting of H2O and the resulting hydrogen and oxygen. Where does that stuff go, right? So let's talk about the ability to split, or as you put it, depressurize water. Talk to me about this. What are plants doing to split water?
yeah, photolysis is the idea basically that light photo can be used to split something. Lysis means to split. Um, so this is where things start to get a little bit complex because the traditional lens of looking at the operation of the oxygen evolution complex is the biochemical lens. We like to look at this from a biochemistry perspective. We say that the light energy comes into the chlorophyll pigments, they absorb it, and light harvesting complexes, reaction centers, there's some energy that kind of builds up, if you will, right? It's not just like you have one photon that enters the chlorophyll and then boom, you have this thing called charge separation that happens, right? There's some stuff that happens. There's a little bit of a charge that has to be built up. Different frequencies, if you work out Planck's equations, different frequencies carry different amounts of energy. 680 nanometers is the one that's a little bit more finely tuned towards what the actual reaction center operates on. 450 nanometer wavelength light, even though it does get absorbed by chlorophyll, that actually does not drive reaction center activity, which is kind of we can unpack that topic a little bit later. But yeah.
Jeez.
So
Real specific spectrums of light doing real specific things and processes within the plant's biology.
yeah. So like what ends up happening is think about it like this. You have basically like a funnel. I like to think about the light harvesting complex as like tuning forks. You ever seen how a tuning fork works? You strike it and then you don't have to have it connected to another tuning fork, but the tuning fork further away will start to vibrate and resonate. And the real question is like, well, how does that happen if there's no wires connecting them? If you're just propagating a wave through space, what's the mechanism there? And that's exactly how light harvesting complexes work. Because if you look at the chlorophyll pigments, they're not touching each other. They don't have direct orbital overlaps, right? So what they're doing is they're not passing the actual electron around. They're passing that excitation energy around. What happens in the light harvesting complex is a photon comes in, that electron becomes excited, and instead of actually exiting the orbit of that chlorophyll pigment, the electron drops back down, and it just passes the excitation energy forward, right? So this is kind of a different concept. In the reaction centers, it's different because you have a direct overlap between two chlorophyll pigments, and they actually share an electron overlap. Now, the name of the game with electron transfer in the reaction center is really interesting, and the best way that I can describe it is imagine you and I are on a swing set, and our swing sets are kind of facing each other. So we have this like arc, if you will, a little half circle, right? So as I swing forward towards you and you swing forward towards me, let's just say there's a certain spot where our orbits will overlap, meaning I could give you a high five or you can give me a high five, okay? Now let's add an element into this game. Let's say I have a ball in my hand, but this is a special ball. I cannot throw the ball forward. I can only throw the ball straight up, and the ball can only go straight down. That's the only motion that it can make, is just along one axis. And if I time it right during our swings, if I throw the ball up while our orbitals are overlapping, you can catch the ball, and now it's in your hand. And when you swing back down to the other side, you're moving that electron away without actually having so there's
Are these the links in the chain?
what was that?
These are the links in the chain that you're describing.
Yeah, and I'm like more so this would be one of the mechanisms behind how the electrons are actually transferred is you have an overlap in the orbital. And the
Wow.
swing set analogy I think would work pretty well. But moving on from there, the in the reaction centers, the electron actually gets moved, right? Once the electron gets moved, that's the actual charge separation event that happened. Now there's this huge hole that's left behind where the electron used to be. It's no longer there, right? So now we have a flavor of protein, or this cluster that we're talking about, this P680 in photosystem 2, that is an extremely powerful oxidizer because it lost an electron and now it wants another electron, right? And this is where things start to get a little bit more quantum. We need to drop the biochemistry perspective and pick up the quantum electrodynamic perspective, because the only way to really understand what happens here and why this is such a profound thing is to look at it from this quantum physics perspective. So here's the kicker about the oxygen evolution complex. The structure itself, the core manganese calcium cluster that looks kind of like a weird chair. If you can envision a chair that has like the seat of the chair along with the back of the chair as well, if you can kind of imagine that with the four legs, that's kind of like the core cluster or the core shape. There are some distortions kind of like along the backside of it, but those are largely irrelevant for the purpose of this conversation. If you can think about just a chair with a large back, yeah, there you go. Yeah, that's a good visualization right there.
We're showing a little picture of it right now, and yeah, it looks like a wacky chair. That's exactly right. So this is the OEC where all this stuff is taking place in this little chair.
Exactly. Yeah. Yeah. And as you'll see there's some manganese ions that are really important. There's one calcium ion that plays a key role, which we'll kind of get into because there's four, they call them COK states, KOK states. There's S4, I'm sorry, S0, which is kind of the initial default state. And then it progresses up to S4 before reverting back to S0. So there's four states, and in each one of these four states, there's a certain amount of activity that happens. And really, the way to think about it is like S0 through S3 kind of like ratchet up and kind of do the same thing, more or less. And really, that transition between S3 to S4 and then snapping back to S0 to the default state, that transition between S3, S4, and S0 happens very rapidly. I mean, this thing happens super, super fast. So it's not a linear progression in terms of what actually happens.
Jeez.
Now, historically, the way that the descriptions, like if you look at some of the more advanced and thorough descriptions from the biochemistry side of things, they'll talk about, nucleophile this and electrophile that, and they'll kind of talk about all these like chemical reactions and substitutions that happen. But I've never seen anybody talk about the field strength, the electric field strength that's generated by the oxygen evolution complex. And to me, that's such an important facet of the operation of the OEC, because to kind of take it back one step, like here's the thing that the OEC does that does not happen anywhere else in nature. The OEC is capable of removing electrons from oxygen. It will oxidize oxygen. It is the only example in biology that I'm familiar with, that I'm aware of, where electrons are removed from oxygen. All fungi, you could pick any fungi you want. All microbes, pick any one you want. Their metabolism is limited to reducing oxygen. They cannot oxidize oxygen. So here we have this perspective shift that has to occur. In nature, the natural default environment is that we have a sunlit atmosphere. If you want to pull up that meme that I generated, now would be a good time to kind of walk through that meme a little bit. So this meme came to mind as I was thinking about like, what is the impressive aspect about, the OEC in plant biology? And I was like, okay, well, plants can lift water out of the ground. That's pretty impressive because we don't see microbes and we don't see fungi doing that. And also we don't see we don't see fungi or microbes being able to break the OH bond, which is also pretty important because if you think about it this way, the OH bond is so stable that it actually defines in a lot of ways the upper limits or the ceilings of plant biology. Think about it like this. You can put so much energy into water that you can physically boil the water, right? At 212 degrees Fahrenheit, but the OH bond doesn't break. It's still OH bonds are present, but it's a water vapor, right? So we've done this phase shift. The bond is still stable with so much energy that would actually break all plant biology. Plants cannot be grown with boiling water. And if you don't believe me, try it for yourself. Put boiling water on your plants and see how fast they die. So here we have the OH bond remaining stable at a temperature with enough thermal energy in the system to break all plant tissue down. By and large, maybe not lignin and some of these more complex compounds, but point being, ultimately, boiling water will kill a plant and OH bond is still stable. How about this? The pH scale, too, is another great example of an upper limit. When we measure the pH scale on the low end, we're measuring acidity based on how many protons, concentration of protons that are in solution. As we surpass a pH of 7, we start measuring the concentration of hydroxyl radicals, which is the OH functional group, basically. What I'm talking about, the OH functional group, is different than this bond strength that I'm talking about. I just want to be clear for people, but it's still the same molecule. It's still what happens when oxygen and hydrogen have a relationship with each other. That bond is so stable that you could be at a pH of 14, all plant biology would die. You cannot grow a plant. You can't even have a cell wall. There's literally not even the most basic biochemical processes are possible to achieve, yet the bond itself is still stable. So here's one for you. How is it that plants are capable of breaking the OH bond apart to begin with? I mean, this surpasses the ability of any known organism to do. Like the amount of energy, for some additional perspective, to break the OH bond, that single bond, requires about the same amount of energy that it takes to boil 2.5 gallons of water or to melt 150 pounds of ice.
Jeez, just
One
in
bond,
one
one
little
bond,
snap that the plant is doing.
one
That's what
bond.
it's. It sounds like what you're describing is really plants' special ability. You know, we, especially on this show, I love talking about microbes, and we talk about all the magical powers of microbes. But you know, you and I were talking off air, and it's like the plants, and specifically their ability to split water, is kind of what makes them magic, what makes them the super beings in this equation. And you described the bacteria and fungi as kind of like, you know, in the Stone Age, rubbing sticks and twigs together.
Yeah. Yeah. They're basically rubbing sticks and twigs together and trying to create fire. And plants are the ones that have the UFOs, and microbes and fungi are painting, they're making these portraits of these alien, figures on the cave
And they don't know
walls. I mean,
why they're
that's
making
the
their
plants.
tributes.
That's the plants that I'm trying to get at here. So the
Wow.
oxygen evolution complex is so special and so unique. Like, never mind the fact that it's the only structure in biology that actually strips electrons from oxygen. That is mind blowing. And like I just said, the amount of energy that it takes. I'm not even talking about stripping electrons from oxygen yet. We haven't even gotten there on our little graph on the meme. I think we're still on the second tier, which is that plants can break the OH bond. Uh, like I said, the OH bond, the stability of that is like, you need somewhere around, what is it, like 500 kilojoules per mole or something like that just to break it. And that's equivalent to this single bond being broken is the same as 2.5 gallons of water being boiled from room temperature, or 150 pounds of ice being thawed back out into a liquid phase.
It's
Again, this
incredible.
is no joke. The oxygen evolution complex is 1 nanometer wide. This is now we're going to start to get a little bit more quantum. Things start to get trippy. Think about the environment that you have to that has to be created, right? This is a structure that's 1 nanometer wide. You could take 100,000 of these structures, stack them side by side, and you would still end up with something that's as wide as a human hair, a single human hair. Maybe a little bit, wider than my human hair, because I don't really have much. But
That's
that,
that's the size of that chair.
yes, the size of this chair is 100,000 times thinner than a single human hair. And it generates enough of an electric field to strip electrons away from oxygen. This is mind blowing. This is nuts. The volts per meter ends up exceeding 1 billion volts per meter. Like, this is not a normal environment at all. So the field that's created polarizes water molecules and generates an electric field that exceeds 1 billion volts per meter. And just to give people some context, you need about 2,000 volts per meter for a lightning strike to discharge. And 2,000 volts per meter is nowhere near over 1 billion volts per meter, right? And on the flip side, on the other end of the extreme, there's something called the Schwinger limit, which a fellow named Julian Schwinger, one of the pioneers of quantum electrodynamics, he was experimenting with very, very high charges in very, very small densities because he was trying to basically rip the fabric of space apart or tickle the fabric of space. And he realized once you get up to about 1.3 quintillion volts, which is like 10 to the 18th power, right? It's 10 with 18 zeros behind it. Once you get to that voltage density, volts per meter, you start to destabilize the quantum vacuum, and you can do certain things like create electron pair and anti-pair. And
Create
you can
antimatter? It sounds like you're going to create a black hole.
well, you basically, like, at that voltage density energy, the stability of the quantum vacuum. It's not so much that it breaks. And we won't get into this because it's not really relevant for us. But you can you can transform energy into matter, basically, and the mechanics of that transformation of energy into matter are, if you've ever seen any of the work done on 0 point energy machines or pulling energy out of the quantum vacuum, anything that actually has merit and is worth looking at is going to pay attention to this Schwinger limit. Let's just say that Schwinger limit is extremely important. This is not a theory. This is extremely real and very relevant. But
And
that's
plants know this, and they go right up to that line, is what you're saying?
they go about halfway between the bolt of lightning and the Schwinger limit. But
That's
let me
crazy.
put it to you this way: the environment that's created in the oxygen evolution complex being approximately 1 nanometer wide, that core structure itself is a chair. There's padding, I guess you could say. There's a house around the chair. Maybe that's how we should look at it. But there's
Got an
other
image of
pieces of
this,
furniture
actually.
around the chair. But the chair itself is about 1 nanometer wide. So if you scale up the 1.2 volts of energy that this oxygen evolution complex is actually capable of generating, yeah, you see it right there. So we're looking at the OEC basically in the center, and what appears to be a complex series of like channels, water channels, I guess you could say, or like water slides, water ramps. The OEC basically is powered by water, and it splits molecules of water apart, but it doesn't do that by classical splitting or the conventional description of splitting. And you know, like I said, we talked earlier about the amount of energy that has to be put in just to boil 2.5 gallons of water, or to thaw out 150 pounds of ice is going to be equivalent to breaking this bond. You know, just a single bond. But the reason also that splitting is not an adequate analogy is because of what happens to water molecules when you actually try to put energy into those bonds. Have you ever tried to put water inside of your car engine?
I've heard that's a terrible idea.
Terrible idea. It's a terrible idea. So here, let me put it to you like this, right? So if you have 1,000 horsepower Corvette, has two turbos on it, and it's made fully forged engine, right? So we're talking about a very solid piece of metal here. It's been forged. It weighs, I don't know, close to 1,000 pounds. You know, I'm not a car guru, so forgive me if I get some of these details wrong. But the point I'm trying to make is we have this extremely strong and rigid metal structure that is designed to handle compression and explosions inside of a controlled environment, right? This is the nature of its operation. If you put water inside of that engine, it's very likely that those water molecules will break the metal. And that's the thing that I'm trying to get at is plants are not in the business of putting energy into breaking these bonds apart, because they know that's a losing proposition. If there's enough water expands 1,618 times or something like that when it's heated up and when it goes from a liquid to a gas. So like if you try to put energy into the OH bond and break it apart, the first thing you're going to do is boil the water before the OH bond breaks, right? We already established that earlier. The second thing is the structure is 1 nanometer wide. If a water molecule expands 1,618 times, it's going to do the same thing that it does to a car engine. It's going to blow it up. It will literally explode this structure. If a piece of metal that's forged and designed specifically to handle explosive reactions will shatter and will break because water says, no, 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 you're not going to compress me. Water molecule will not compress. It will break the metal before it compresses, right? So what do you think
Right.
would happen to a plant structure, this small little 1 nanometer, 100,000 times thinner than a human hair that has no metal, by the way? It's like making a particle decelerator of toilet paper is basically what's going on here. And
Yeah, man, you're gonna end up with the hydrogen bomb at that point, right?
boom, there we go. Yeah, so plants are not splitting molecules of water apart. What they're doing is they're polarizing. They're bringing water molecules into an environment. This electric field that's created within the oxygen evolution complex is so powerful that it polarizes the water molecules and it allows them to sequentially depressurize the water molecules. They don't violently release it. What they do is they gently unravel. They gently release the electrons and they release the protons. The most interesting part about this operation, like I said, the fact that it happens is the only example in nature where you have a primary metabolic pathway that is built specifically around taking electrons away from oxygen. This is no joke. I mean, there's a reason that when we talk about redox chemistry, the term oxidizer or oxidizing, the reason the term oxygen is used there is because in nature on this planet, there's only two things that you need to create a default environment. One is you need sunlight, and then two is you need oxygen. We have that in the atmosphere. We have a sunlit environment, we have a sunlit atmosphere, and we also have about 20% oxygen in the air. So like the default state of this environment is things get oxidized. That's why when we look at the nutrients in the soil, we find nitrogen is oxidized in the form of NO3, sulfate is oxidized in the form of SO4, even carbon is oxidized in the form of CO2. Everything by default will get oxidized, including water molecules. If you just leave a glass of water out, it's the electrons and the way that the photons from the sun interact with the electrons and the oxygen kind of creates this environment by default where oxygen wants to pull electrons towards it. This is the natural default state of biology. That's why we have this term called oxidizing, because the general trend is for the electrons to move towards the oxygen. And that's also why all of your fungal and your microbial metabolic pathways, they move the electrons to oxygen. When we talk about mitochondria, it's oxygen is the terminal electron acceptor, right? We know that the oxygen is going to grab all the electrons, because if the plants if the microbes and fungi try to move against that thermodynamic gradient, it's almost like the electrons roll downhill towards oxygen, accepting it, right? But plants, they can push those electrons uphill. They can take the electrons off of oxygen, and then in the mitochondria, they can take those electrons and put them back onto oxygen. This does not happen with any other organism. Microbes don't do it.
Wow.
Fungi don't do it. Fungi and microbes are at the mercy of oxygen. That's why all of their metabolism says, here you go, you can take the electrons. They cannot move against that gradient. They cannot overcome that. But the oxygen evolution complex is the one example in biology where we find plants stripping electrons away from oxygen. They produce the molecular oxygen, and then in the mitochondria, they may actually recombine. They may reduce that to produce the peroxide or the water or whatever it is that they need to produce. They can oxidize oxygen, and they can also reduce oxygen. So oxygen to them, when we were talking earlier about reactive oxygen species and the role that oxygen plays in redox chemistry, the real aha moment is realizing that plants can do it both ways. They can take the electrons off of oxygen, and they can also put the electrons back onto oxygen. This does not happen with microbes and fungi. The other important thing that I want to mention about the oxygen evolution complex is this idea of depressurizing water molecules that become suspended in this intense electrical field. I mean, a billion volts per meter is no joke. This is insane. The thing that ends up happening is the electrons are gradually removed. At first, it's the protons and the hydrogen. There's something called proton coupled electron transport, PCET, that occurs. That's sort of like a charge balance, quantum scale charge balance mechanism for the plants. But the idea is like, hey, you've got the protons, you've got the electrons, and they're kind of like, they need to be synchronized, but they're kind of doing their own thing, right? Because we don't want charge recombination to occur. If you remove the proton, the last thing that you want is for that proton to come back and be recombined. Same thing with electrons. What we don't want is for the electron to be stripped and then to fall back down. Or alternatively, and this is where it gets really impressive with the oxygen evolution complexes, we're removing electrons away from oxygen, which creates radical species. It creates radical oxygen species that are missing electrons, and these are the strongest oxidizers in biology. These are the things that will literally rip electrons out of DNA, and they will cause irreversible damage. Like, this is no joke. What plants are basically in the process of their normal metabolism, day-to-day operations, they're basically making the most reactive species of oxygen that are possible to make in nature, and they're doing that in an environment where they can control perfectly and precisely the recombination. So the oxygen, even though it's radicalized, meaning that the electron was stripped from it, the oxygen is suspended inside of this intense electric field, and it cannot get the electrons. This is not normal. This is so far away from normal. This is the one and only instance where it happens in all of nature. And the power that's required to actually achieve this surpasses the amount of energy that's released in a lightning strike. And yet we're only talking about something that's 100,000 times thinner than human hair, but it generates more volts than lightning bolts that stretch for miles. Like, I need people to understand this. This is not a normal environment. This is some alien spaceship technology. This is why the microbes and the fungi are like rubbing sticks and rocks together, making fire. And the plants are like, oh, that's cool. I'm taking electrons off oxygen. And to boot, they lift the water up, they take the electrons off of the oxygen in an oxygen-rich environment. This is the mind-blowing part. Like, they do this in the aerial portions of the canopy. Less than 100 nanometers, or, some very small distance away from the oxygen evolution complex is this environment that is by default going to oxidize everything. Everything gets oxidized by default, right? Except for the oxygen evolution complex. It's almost like the atmosphere has a window into the plants, and the plants are like, hey, you see what we're doing here? You see all this oxygen? Oh, we're going to take the electrons off of the oxygen. And the oxygen can't do anything about it. It's stuck. It's polarized. It's suspended in this field where it can be a radicalized species, and it doesn't do anything at all. It's completely tethered. Now, what ends up happening in that S3, S4 state, once the protons and then the hydrogen has been stripped and removed, once that OH bond has been broken with sufficient energy to boil 2.5 gallons of water, you have two oxygen atoms that are extremely, extremely reactive. And the calcium, if you look at the actual chair, there's a piece of the actual chair, one of the pieces, or one of the corners of the seat, I should say. One of the corners of the seat, the calcium has a very specific ionic radius. You can actually swap the calcium out with something else, but that specific ionic radius is like a bridge that is the perfect width to connect these two radical flavors of oxygen that are just so hungry for electrons that if they existed in any other environment, they would lead to irreversible damage. Like, they're so reactive, they would probably kill the cell that they were in.
Man, Okay,
But
so this go ahead. Sorry, finish your thought. And then I
yeah,
got some.
just to really quickly finish up, that calcium that sits in the center participates in that last step of the cycle where the two oxygen radicals kind of are quenched with each other. They meet each other, they are forced together, they snap together, and molecular oxygen is produced that is non-reactive. This is mind-blowing stuff. This is not normal biology at all. This is so specialized that once again, plants are the only ones doing this. They're the only ones with the plasma cannons. That's it.
Yeah, exactly. The plasma cannons. It's a great way to put it. It's really clicked for me, man. There's a lot that I've picked up on here. I'm going to enjoy editing this one back and listening another time over. Um, let's bring it to some analogies and some applicable tips. First, starting with this idea of the way you're describing oxygen in general. It seems like oxygen is a little bit unhinged. It seems like oxygen is like you said, it's everywhere. It's kind of popular in that regard. But you've also said that oxygen is like a little bit selfish sometimes. How should we personify oxygen in all of these kind of scenarios that you're presenting us?
Yeah, I mean, I guess the easiest way to understand would be like oxygen is like your friend that always shows up to the smoke sesh, but he never brings anything. He's always taking your stuff, and no matter how hard you try, it always ends up getting passed to him, and you're just like, man, no matter how hard I try, I can't get this joint to not get passed to oxygen over here. That's what oxygen does with electrons. It somehow finds a way to never give up its own electrons, but it always takes your electrons. Always, 100% of the time. It will take electrons from anything and everything that it possibly can. And again, going back to the microbial and fungal biochemistry, they know this. This is why they freely give the electrons to the oxygen. They're like, you know what? You're going to take it anyways. And if you're not going to take it by choice, they take it by force. Reactive oxygen species, when you don't give oxygen the electrons that it demands and that it thinks it's owed to it, it will come in like the IRS and it will just take what it wants, you know?
Rooted leaf nutrients. If you aren't totally satisfied with the nutrient regimen that you have, you got to try rooted leaf. No pH required. Mix it, use it, water it to run off. You're going to see amazing results. Listen, I've been using rooted leaf for a few years now, and it's an absolute game changer in my garden. It's loaded with carbon. Like I said, there's no need to pH it. Just mix it and feed. Watch the plants explode. Plus, you got a brand new product, Microflow is dropping. This is their micronutrient product. Use code GrowCast for 20% off your rooted leaf order. You got a free bottle of Microflow. So that's it, everybody. An extra gift plus 20% off. It's rootedleaf.com. Use code GrowCast. Grab that new Microflow. Let me know how you like it. And huge shout out to Rooted Leaf. Thank you to Nick. Thank you to all you supporters out there. Rootedleaf.com. Code GrowCast for 20% off and a free bottle of Microflow. So that really is what clicked with me, man, is this idea of oxygen affecting everything around us downhill, as you described. That's why you said water, increases in oxygen over time. Rust, looking at rust on metal, right? Same idea. And then plants are the only ones that are capable of going the other direction and pushing it back uphill. That was a big breakthrough for me personally. And on that note, let's talk about that incorporation of oxygen into water. Super, super applicable for home growers here. Nick, why do we, with all this in mind, why do we aerate our water? I can't tell you how many times I've seen a plant become so much happier just because we introduce some air through a bubbler into the water before we feed it. Why is that?
Yeah, I mean, dissolved oxygen can help roots breathe. The roots of a plant are just like human lungs. They actually need oxygen to do their thing. They don't photosynthesize. Obviously, there's no chloroplasts in the roots. So a huge portion of the benefits come from just the additional presence of dissolved oxygen being there and allowing the proper oxidative phosphorylation to occur. Like I was
putting an oxygen mask on for ourselves, it's going to increase our endurance and our performance and everything.
Exactly. And then the other part too is that when you have oxygen present in the soil, it can help drive soil chemistry by facilitating some redox chemistries too. It can help with certain things, like if you have really compact soil, like if you packed it down really tight and there's not a lot of air and maybe the roots have trouble pushing through the soil and growing, having well aerated feed water can actually kind of help bring more dissolved oxygen in to kind of help counteract that presence of, not enough gases being present. And also to some extent, it can help create these microstructures in the soil where the oxygen itself, because it exists in a gas form, and it's introduced into a solid phase, which is basically your soil. So you have almost like this effect of the oxygen that's in the water trying to expand and push out on the soil a little bit to help aerate it, to help expand it, to help lift it up so that the roots can start to breathe a little bit more naturally. This is why saponins work so well to increase aeration capacity of soils.
Man, that's good stuff. A lot to chew on here. I love the idea of this splitting of the water being this powerful act, but like you said, kind of just an unraveling. Instead of, smashing the lock, you just simply untie the knot. And that's there's so much here, man. It's like I've been talking about the principle of correspondence. And there's so much here that corresponds to life and physics and nature. And you're zooming in very small, but this applies to as big as you want to go, all the way out to the universe. You know what I mean? So this stuff really flips
Yeah.
my cookie, Nick.
Yeah. And I like that you like this graphic that you have right there is actually really good for me to kind of make this next point. So we're looking at basically here, this is the photosynthetic machinery, if you will, right? We're looking at a thylakoid membrane, which is basically like a phospholipid membrane. You've got, a head pointing up and a head pointing down. And in between, you've got two, the tail groups basically opposed to each other. So everything that we're talking about with photosynthesis is actually embedded within the membrane. And this concept of as above, so below applies really well to what we're talking about here. I want to try to make a point about this scale-dependent paradigm shift that is really important. When we looked specifically at the function of the oxygen evolution complex, I said that there's some quantum stuff happening here for sure. You can only describe the operation, like what the oxygen evolution complex does, like the fact that it strips electrons from water. It can break the OH bond without actually putting energy in to that bond. Like this stuff is not normal at all. It's so far away from normal that this is the only instance in biology where this is the case. So we cannot just talk about, we have to first understand that there's an environment where these reactions are happening, right? That environment is not normal at all. And this environment is field driven. This is where quantum electrodynamics actually becomes the paradigm. The oxygen evolution complex, that chair-like structure, is 1 nanometer wide, generating about 1.2 volts. We scale that up, we get over 1 billion volts per meter. Nuts, absolutely nuts. If we scale up from the OEC, because keep in mind, photosystem 2 is embedded in the actual thylakoid membrane. Now we have another example of a membrane where we have, everybody knows you can separate charges with this membrane, right? So on one side, you have charge being built up. You see the protons accumulating on one side. Those drive ATP synthesis, leading out into the stroma. So here's another example of maybe a field that's very important for us to pay attention to, because the thylakoid membrane has a charge potential. It's different on one side of the membrane than it is on the other side of the membrane. Now, because it's not 1 nanometer wide, it's actually maybe, let's say, 10 or 20 nanometers wide. The voltage potential is lower than the oxygen evolution complex. So field strength is still very, very important in terms of figuring out, because we see protons being vectorized one way, right? And we see electrons being entered into the electron transport chain from the oxygen evolution complex. We didn't see that in that infographic, by the way, but just so that we're clear, when we talk about like this OEC and what it does, yes, it depressurizes the water molecules to release the electrons, to release the protons, and to release the oxygen as molecular oxygen. The way that those get released is different depending on the environment of the field itself. Those electrons basically are forced by the strength of that field to go one way. The protons on the other side are forced to go another way. So you have this clean split, if you will, of the electrons and the protons and so on and so forth. When we scale up and out, we see the same kind of principle being held, right? As above, so below. We saw this microscopic thing with the OEC. We zoom out and we see just like the OEC exists inside of this larger thing, but the larger thing also happens to mirror kind of the same properties. It's not as strong voltage. It's not as extreme as far as the field strength goes. And we're not witnessing oxygen being radicalized and not recombining spontaneously. That doesn't happen anymore, right? So now we're starting to shift our paradigm away from quantum electrodynamics into more biochemistry. Now we're looking at things like, instead of looking at field strength to dictate how electrons are stripped off of oxygen, we go to classical descriptions of redox chemistry, just classic electron transfer. And as we continue to work out from the thylakoid membrane and even in the mitochondria where the electron transport happens, if we zoom out and we start looking at the cytoplasm, that's where field strengths perhaps diminish even more. Now, instead of just electron transfer, now it's acid-base chemistry. It's protons and pH becomes very, very relevant, right? So on the quantum scale, it's field strength, it's joules, it's coulombs, it's all this stuff that has to do with like very, very nuanced stuff. But we start to zoom out and we realize, okay, once we stop talking about that, now we start talking about redox chemistry with electron transport, but it's only relevant in the transport chain where we still have this large field strength and the large voltage present, right? We don't talk about electron flow outside of the electron transport chains, right? When we're talking about normal metabolism in plants, we're thinking about chemical reactions. We're thinking about acid-base chemistry, so on and so forth. Paradigm shifts, basically, is what I'm trying to say.
And the scaling is really interesting, man. You're saying it's chairs all the way down, and they're exactly. Slightly different chairs.
Yeah.
But if you zoom out, it's the solar system is just another chair. and it's interesting when you talk about the scale of the power. You know what 1.2 volts at 1 nanometer adds up to if you scale that up. Now, this just gets us to splitting the H2 and O. That's literally all this gets us to. What are the fates of those? What ends up happening to these molecules that the plant takes up? I know at one episode it kind of seemed like you were saying these end up terpenes in some cases.
Downstream, yeah. So like just in terms of the core photosynthetic machinery, what we've talked about and where we've traced things out so far is that the light energy has hit the chlorophyll pigments. The chlorophyll pigments have started vibrating. They get all excited, right? There's this tuning fork kind of thing that the energy gets funneled inward, and something called charge separation actually happens. This is the actual dedicated step of photosynthesis where the electron is no longer just bouncing up and down. The electron actually leaves the reaction center. And because it left, there's a hole that was created that the oxygen evolution complex needs to fill. This is where the process of depressurizing water molecules actually comes into play directly, because once the charge separation happens, the electron that has to come in is sourced from water molecules. So in the oxygen evolution complex, we create this intense electric field, depressurizes water molecules, releasing the electrons. Those electrons get funneled back into the electron transport chain. From photosystem 2, it'll go to photosystem 1, and then from photosystem 1, it'll go towards what we call, what I like to refer to as the electron sink of that transport chain, which is NADPH. You guys may have heard me talk about this before, but that's the molecule that receives the electron and stores it. And then from there, it kind of acts like a flywheel or a centralized hub to distribute that charge out. So NADPH, yeah, there you go. It's on that graph right there. So we see light energy coming into chlorophyll, this cool stuff happening with the electrons. This graph is just a pinch misleading here, but what ends up happening is light energy comes in, the electrons are harvested by depressurizing water molecules. Those electrons get entered into the transport chain where they ultimately get sunk into NADPH. NADPH is very important because it's one of the requirements of the Calvin cycle. So in order for plants to take CO2 out of the air, they need the NADPH. Well, where does that come from? This is where the water gets split. The electrons make the NADPH, right? Now, we also have protons being split from the water molecules. So where do those go? Well, it turns out that those participate in forming the proton gradient that makes ATP. ATP is the second component of the Calvin cycle. So we have electrons leading to NADPH, that's required. We have protons leading to ATP, which is also required. And then the third component of running the Calvin cycle is CO2. The plants need NADPH, they need ATP, and they need CO2. So the CO2 gets released to the active site of rubisco in conjunction with ATP and NADPH. And it's really the trifecta of everything coming together. It's the spark and the air and the fuel being timed at the exact same moment that the engine actually has that bang, and it creates soluble forms of carbon for the plant. If you have something mistimed, like if the plants were to deliver ATP and NADPH, that's great, but they just delivered the spark with no fuel, so no work can be done. Yeah, it's the exact same kind of thing with the plant. So that we've kind of traced the flow of the electrons. The molecules of water get split apart, and it's really the protons and the electrons that go off and do their own separate thing. But if you traced what I just said, you realize they actually come back together. The electrons and protons get split apart. One goes to the electron transport chain, one goes towards the proton gradient, but both of them end up coming back into the Calvin cycle where they participate in carbon fixation. So it's charge separation, charge transfer, charge storage, and then charge recombination. All of this stuff is just passing protons and electrons around. We didn't even get into proton coupled electron transport, but there's instances where you have hydrides like with NADPH, for example, that reduction, it's not just a single electron being moved towards NADPH. It's actually 2 electrons and 1 proton that go. And there's the coupling of protons and electrons to maintain a charge balance. But even that kind of varies, because in the initial stages of photosynthesis, you've got single electron events, but transferring single electrons can be very risky business for plants. They couple single electrons with protons, or they do 2 electrons with 1 proton in some cases. And only at the sites of like as we approach the light harvesting complexes and the reaction centers, it's only in those specific instances do we actually see the single electron transfers, because those are the ones that are extremely dangerous. And that's why plants have to produce the field in the oxygen evolution complex that approaches 1 billion volts per meter, because in that environment, that's where oxygen becomes predictable with its electrons. And if you're below that, oxygen is going to do something unpredictable, like take all your electrons and kill you in the process. So
only plants can keep oxygen in line. Oxygen is going to all these different parts, shows up at every party, at every smoke circle, takes everyone's weed happily at the smoke circle. And if you don't give it up, he'll actually check you. He'll punk test you and take your weed.
Yeah.
And then only plants are able to provide an environment where now oxygen is like, all right, just kidding. I'll listen to you and you only. So it seems like plants are the masters of oxygen.
Yeah, and it's not like, oxygen isn't just that one guy that walks around doing the stuff at the party. It's the guy that walking around doing that, and he's a 3rd-degree black belt, and he's a world-class bodybuilder. He's Ronnie Coleman in his prime, basically. Like, how are you going to stop oxygen from taking electrons? It doesn't happen in nature. That's why the term oxidizer is, they're just like, we might as well name it after oxygen, because the thing that oxygen does is the behavior that we're trying to describe.
That's
Oxidizers
so cool.
do the thing that oxygen does.
Super reactive too. It's just I'm starting to understand the personification of oxygen and what it does.
And then plants come along and they're like, "Oh, you're cute. You think you could take these electrons? Here, let me show you." And then the plants say the plants will lift the oxygen up into the air where all of its friends surround it.
Like Darth Vader. The plant uses force power. The only thing that could beat Ronnie Coleman would be would be Darth Vader.
Exactly. It would be like, it's seriously like supernatural levels of power are achieved in order to do this thing. But for plants, it's normal. It's totally normal for them. It's so normal. It's for them to just part of their normal day-to-day operation is they're just like, yeah, oxygen, it's time for you to, get your electrons removed from you. And it's the only instance in nature where that happens.
Here's what I want to know, Nick, that I'm sure you'll be excited about me asking. How does all this quantum physics stuff, how does the OEC, how does all of this play into your work on Rooted Leaf Gen 3? Because you guys just dropped a whole new, improved, like I said, man, your line is the best line out there, in my opinion, as far as liquid nutrients go, hands down. And I know you've made improvements to that. So, and I also know that a lot of this information you're talking about spawned from that work and research and development. So talk to me about how it ties into Gen 3 and these products that you've dropped.
Yeah, the easiest way of looking at it is to say that Gen 3 Rooted Leaf is engineered out of the equations like Planck's equations, Einstein's energy mass equivalence. When we get into quantum electrodynamics, there's 3 other, there's Feynman, Schwinger, and Tomonaga that came up with that. And basically quantum electrodynamics states it's a field of science that deals specifically with how photons interact with electrons. And I can't think of anything that's more directly related to photosynthesis than like how photons interact with electrons. That captures everything about plant biology. If you think about, you want to talk about the effects that ultraviolet light has on plants and the detrimental effect it can have, or the amount of stress that can be generated from UV light, that's literally just photons riding in on a particular frequency. They carry a certain amount of energy, right? If you work out Planck's E equals HV, you can calculate the amount of energy that comes in off 280 nanometers, or, if we're talking about like 450 nanometers, 680 nanometers, that energy load ends up being like 2.45 volts to about 1.8 volts, depending on which spectrum. So like you can use these equations to quantify the amount of energy that's being carried into the plants. And then if you understand Einstein's work of tying energy and mass together and saying like, okay, there's a relationship between energy and biomass, right? Extrapolating forward, you can lead into, well, there's a relationship between the concentration of terpenes and cannabinoids and energy that went into the plant, right? That's why we have to grow these plants under high intensity environments. We can't grow them in the shade off to the side. They're never going to hit 30+% cannabinoids, because at the end of the day, it's a physics-based approach to increasing yield and quality. So I haven't seen other people do engineering work out of these equations. The closest that I've seen is lighting manufacturers. They got wise to it a few decades ago. Certainly, they started looking at manufacturing different lights based on these understandings of chlorophyll and really everything that we know about plants and how chlorophyll works, how pigments absorb particular wavelengths of light. That is ultimately rooted in quantum electrodynamics already. It has to do with how photons interact with electrons. And so it speaks directly to the heart of what's going on in plants, but no one's done engineering work specifically for that. So like that was the approach that we took was, can we incorporate some real like quantum physics, quantum electrodynamics into the engineering work that we're doing, and can we like lift these equations up into something that can actually be there's some benefits to the plants going on for real. So a lot of this has to do with creating optimizing environments, I guess you could say, so like what we were talking about with the OEC, the fields, and just figuring out ways to do certain things like wireless transmission of power to the plants, because these types of things are definitely possible to achieve. And I will say, like a lot of stuff we've been kind of leading up to, we've already been kind of hinting at and doing this already, but with the latest and greatest versions of the products, it's really just like based in physics equations now. And really what we're doing is just trying to drive a lot of carbon to the plants in a way that modifies the way that I'll put it is like, for if you read the blog post on the website, it's pretty lengthy and it gets into detail, but one of the things that I try to really stress to people is plant biology seems to be wrapped around a series of processes that are not biologically driven in their origin. One of the examples would be, plants use the power of the sun. Yeah, that one right there, the welcome to Gen 3 post. It is long. I would encourage people to just break it up into various chunks and read it slowly. But the idea that, the thing that I'm trying to convey is this plant biology stuff seems to be wrapped around processes that occur passively. So plants aren't trying to put energy in to overcome kinetic barriers. They're not trying to say, like, let me move against the grain and let me cut against the grain here. Really what they're doing is they're creating environments where the things that happen in nature happen way more predictably in plant biology, and they happen in a way that the minimum amount of energy going in is required to catalyze that. That's why when we look at the oxygen evolution complex, we see, ironically enough, that represents that, and it also stands in stark contrast against it. But it represents it specifically because plants aren't putting energy into the water molecules to break them. They're creating an environment where the electrons naturally depressurize and fall apart, because the alternative is putting energy in, and that would create an explosion. And plants aren't going to put that amount of energy into a structure that's 1 nanometer wide and have the water molecules expand 1,618 times. That would blow up the engine. So we see instances where plants are taking advantage of natural phenomena, and really the biggest changes that went into our products, as far as like a functional basis, they're specifically designed to modify hydration chemistry and create structured water microenvironments and create these fields where you can have charge transfer events occurring outside the context of plant biology, which also this charge transfer thing includes the wireless transmission of power and increasing photosynthetic yield to plants as well. I mean, it sounds a little bit foofy, but in reality, like if you understand the equations, you understand the math, you're just like, oh dude, this is totally possible. We could totally do this.
It's just blowing my mind that you think about it this way, dude. That's so cool. You're like, wireless transmission of energy is like, do you really think about this different than anybody else out there? And I think it's so fucking interesting, man. Yeah. And I'm not surprised that the product shows out in the end.
Yeah. So, and we'll get to a spot where we'll disclose a little bit more about what we're doing right now. It's like, it's kind of wrapped up with a lot of the stuff that's, it's very complex just in terms of the manufacturing side of things. Like, this stuff is not easy at all to do. Like, I want people to also understand, we manufacture everything ourselves. Like, the stuff that we're doing is stuff we ourselves do from scratch. And a lot of the chemical reactions, a lot of the chelation chemistries, a lot of the fermentation stuff that we're doing is so not normal, like in terms of how it's typically done or conventionally done. So like, we develop these processes specifically to accommodate the process flow, so to speak. We're not trying to shoehorn the process flow into how our equipment works. It's actually kind of the opposite. Is we need the equipment to be built around all the stuff that we're trying to do. So that's why I've just been a little bit more hush hush about it while we dial in exactly what's going on. But what I can tell you, as a matter of fact, across the full product line, is all the products are way more dense. The carbon load in silica more than doubled. It went from 4% to 9%. So the total carbon more than doubled on that. For peak bloom and for resin bloom, both of those NPK analyses stayed the same. Peak bloom is still a 0.76, but the carbon load increased from, I think, 8%. It went up to 13% in total. So it nearly doubled on that. And then same thing for resin bloom. I think it went up from 6% up to 13% as well. So there's a lot more carbon inside of the products now. We can exceed 5,000 ppms of CO2 equivalent carbon. And then, yeah, for the A and B in particular, there's more magnesium now, and those both got a pretty hefty increase in carbon as well, about 25 to 33% bump. And that carbon, again, like the carbon containing materials that we're working with, these inputs, it's still fully plant based. There's no animal byproducts. They're still all natural. I don't know if they would be, considered compliant with organic agriculture, just because, like, I tried looking up NOP guidelines to see if these products and the new, chelation chemistries and all that stuff would be eligible for organic certification. And like, there's literally I can't find a yes, no, or even a maybe. This stuff literally does not exist in the NOP guidelines right now. So I want to try to be a little bit mindful about how we roll out the descriptions. But yeah, just so that people know, there's substantial changes to the way that the products behave, how they handle. If you shake the bottles, you'll see they come out a little different. And then the feed water itself too, if you make the feed water, you'll see the way that the feed water holds itself together is just way different now too.
It's really interesting that you put local and like sustainability from a business standpoint and American sourcing from a business standpoint. For as long as I've known you, and you said when you started the company, that was a big deal for you guys. And then you look at the stuff that's happened over not just the past few years with trade stuff, but the past 5-10 years with trade stuff. And man, you put yourself in such a good position. You guys are making that yourself. It's unlike any other product. You're not just ordering in salts from God knows where. And look, it's paid off. It's paid off for you, man. And your product really, really works. So code GrowCast saves you 20% at rootedleaf.com. What can we say about Microflow? This episode, sorry, I was just checking my phone to check the calendar. This episode's going to be dropping June 23rd here at the end of this month. Mm-hmm. So what's the deal with Microflow? Will that be available when people hear this?
Yeah, we'll probably have Microflow launched by the time people are listening to this. Microflow was a really interesting product for us to develop because the micronutrients were the one sort of product category that we didn't have. It was always in Primer B. We always had enough micronutrients, but over the past couple of years, I've kind of noticed that there really is a good fit for this kind of product. And it's one of the ones I spent a pretty long time just thinking about how we could formulate it and how we could do it, because micronutrients are interesting. If you look at the parent sulfate forms of the micronutrients, like your iron sulfate or your copper sulfate, your manganese and your zinc sulfates, most of the sulfate forms of the micronutrients are actually more soluble in water than some of the like organic acid chelates and so on and so forth. I mean, the amino acid chelates are really soluble in water, but my point is basically the sulfate forms are really inexpensive, and they happen to be so soluble in water that you can easily correct micronutrient deficiencies without having to do any of this fancy chelation stuff that you find with micronutrients. But having said that, there's still I kind of looked at that and I said, well, I don't want to just like chelate or complex some micronutrients and have it cost more than sulfates, which are still have efficacy, right? People can use the iron sulfate, and yeah, sure, some of it may get tied up, but it's not going to damage the soil. It's not going to kill your plants. And in reality, you can correct these micronutrient deficiencies without the fancy chelation chemistry. So how can we make a chelated, complex micronutrient product that still has significant benefits, not just in terms of solubility, but like the impact on the plant? Can you apply this and have it immediately go to work? Can you apply it and have it not burn the plants if it's 100 degrees outside and it's 2:00 in the afternoon and the sun is just beating down on the plants directly overhead? So these were the kinds of form factor things that I wanted to solve for, because it wasn't just about solubility. I mean, in reality, the micronutrients, you only need like 10 to 15 ppms, maybe 20 of iron, and then way less of everything else. You need fractions of a ppm of boron and copper. So like to put all this in solution is not going to budge up against any solubility limits whatsoever. People will not run into the solubility maximum before things start falling out. Like you're going to be 10,000 times over the proper dose of your micronutrients before you run into solubility issues. So
Yeah, we've seen it time and time again, and you help out a lot in the Discord, in the member Discord. I appreciate that. With so many lines being so good now, and so many soils being so good now, you see these plants that just want a little more of this or that mineral. And when you take a look at how little boron is in the soil, and who knows if that's available. Sometimes you just need a dash of manganese. Sometimes you just need a dash of these products. And that's why I'm excited for Microflow, just to get those all in one bottle and at a very concentrated level too.
Yeah, yeah, and it's specific for high intensity environments. The idea with putting so like specifically the micronutrients. One thing that I saw when I was doing the formulation work was looking out and just seeing the landscape of opportunity. Like if I was a grower and I wanted to buy some micronutrients, what could I buy out there on the market right now? And I kept looking at these labels and I saw there's no rhyme or reason. I mean, at least when we're buying CalMag, we kind of know like we got more calcium and we got less magnesium, right? And we can kind of anticipate a particular range of calcium to magnesium. I've never looked at a CalMag product and saw 9% magnesium, 0.5% calcium. It's just that's not how the formulas work. But with the
So true.
micronutrients, they're all over the place. I've seen micronutrients with way more copper than boron and less iron overall. And I'm just like, this is not how plants work at all. So let me just kind of clear the air a little bit. Let's get to a spot where we can clarify why exactly these micronutrients are relevant in the doses that they're relevant in. So for our formulation, it goes iron, manganese, zinc. Those are the three that are most important and in that order. We need the most iron, followed by manganese and zinc. The ratio between manganese and zinc is going to be pretty close to 1-to-1, but there's a little bit more iron there in general. So why is that? Why those three and why those three ratios, right? Turns out when you increase the light intensity, iron gets the most immediate draw, because where we find iron going to when you put iron on your plants, most of that iron is going to go towards this electron transport stuff that we were talking about in the membranes, where all the electrons are being passed around. Well, iron is one of the hubs for that to occur, for the electrons to kind of be passed on around. It's just like a wiring system in a car. You've got the electrical components that require a little bit of power, but they don't need the full load of power at once. So the iron will function like a wire to basically extend the correct amount of power that's required for each of the individual components, whether it's the speaker system or the lighting system in the car or the heated seats in the car. Like all these individual systems will draw on power that is carried by an iron containing compound. Usually they're iron sulfur clusters in the electron transport chain. Manganese and zinc are also useful for the same thing. We mentioned manganese is a component of the oxygen evolution complex. So for plants to depressurize water molecules requires manganese. It's actually the thing that goes through and does the charge holding and charge transfer. So you can think about it like a flywheel that rotates, and every time that it rotates and it clicks, it captures an electron and then it shuffles the electrons off. So it's there, it's sitting there, it's spinning, it's building up the charge, and then it's letting go of the charge. And then zinc releases CO2 to plants. So those three are really important, right? It's anytime that you turn up the light intensity, anytime that your plants start drinking more water, and anytime that you want to give more carbon or CO2 to the plants, you can be sure that iron, manganese, and zinc will be needed in very, very slight increase. I'm not talking about adding 10 ppms extra or 20 ppms. I mean, even 1 ppm extra or 2 ppms of iron, for example, the tiniest little bit extra can help go a very, very long way. So those three are the major ones. After that goes boron and copper. Those two are in the back seat, so to speak. When we look at the ratio of boron and copper to the ratio of iron, manganese, and zinc, we find a huge difference. There's like 10-to-1, 20-to-1 ratio. So I would consider the boron and the copper to be like the micros of the micronutrients, right? The iron, the manganese, and the zinc, those are the big boys. Those are micronutrients, but they're the most important micronutrients in terms of the quantity that we want to deliver. The boron and the copper are fractions. We need like 1 ppm, maybe 2 ppms of boron, and then we need like 0.5 ppm of copper or 1 ppm of copper as well. So that's the form factor for this micronutrient product. Is it's done with the anticipation that people who are growing in high intensity environments are going to increase their lights, they're going to have plants that drink more water, and they're going to try to give more CO2 to those plants that are being grown. And that's what the micronutrient product was specifically formulated for.
Man, you really hit it out of the park. You're so right, by the way. All the micronutrient products having different levels. And really, with these high intensity LEDs, that's where I saw a lot of these deficiencies kicking off with my members. And, those are the ones that run short. You're just slamming them with these LED manufacturers that have been competing each other competing with each other for the most efficient and powerful light. So yeah, what I would also say is not only just the idea of seeing deficiencies and then correcting them with the little microflow, but also since I started seeing that so much, I've just been preemptively supplementing. You don't have to wait. You shouldn't wait for a deficiency. Like you said, there's so many things that can help. I'll hit them once in veg, maybe twice in veg and a couple times in flower too, with that micronutrient boost. Not too much, just like you said, but it seems to really do wonders in like keeping them perfectly even green, praying, and achieving their maximum potential. So
Yeah, and it's a really concentrated product too. The functional use rate is as low as 1/10 of a mil per gallon. So you could put 1 milliliter in 10 gallons of feed water, and you would get enough micronutrients to maintain a happy plant. If you're not deficient, but you don't want to become deficient, you're not interested in a heavy enough dose to create toxicities or create lockout or anything like that. You can safely add 0.1 or 0.2 mils per gallon with every single watering, and that will just be maintenance mode. That won't create any problems for the long term, and it won't allow for any deficiencies to be created either. But let's just say hypothetically, you got something going on with the soil chemistry, and maybe the batch wasn't made just right, and you determined that you're completely missing micronutrients. You don't have any. You're not just deficient. You've got 0.00 ppms of iron. You're like, I need this deficiency corrected right now. You can use this product as a foliar spray. You can do 1 to 2.5 mils per gallon, and that will immediately correct any micronutrient deficiency. Put it this way, if you watered in a use rate of 1 mil per gallon, you would be able to correct any micronutrient deficiency. And if your plants still have some signs of stress, it's not going to be related to micronutrients. Let's just put it that way. At 1 mil per gallon, you will immediately and quickly correct even a severe deficiency. And you can also use this product as a foliar spray too. So foliar spray use rate, kind of same thing. You could do 1 mil per gallon. You could do 2.5 mils per gallon. That'll correct a deficiency. Or if you want to do maintenance mode, you could do 0.5 mil per gallon as a foliar spray. That'll work great. I do recommend people try using this product as a foliar spray during the first 2 to 3 weeks of flowering, during that stretch phase, because there's a lot of things that happen with iron, manganese, and zinc specifically. And it's not just the functions that I mentioned with, electron transport, water splitting, and CO2 supply. There's other functions that are present as well. The micronutrients like manganese and zinc can also participate directly in antioxidant systems. So if you crank up light intensity, one way of reducing that oxidative stress is with those micronutrients as well. And then also I want to mention that zinc is required for genetic expression. Usually for the first 2 to 3 weeks of flowering, you have changes happening, like genetic changes, expression changes. And those expressions are being driven by enzymes that contain zinc, called zinc finger protein. Molecules are zinc finger proteins, and they basically go and they kind of like snip up different sections of the plant's DNA, and they allow for that section of the DNA to be expressed. So if you want to get slightly better expressions, or just like a more well-rounded expression, or just like a faster snap between the veg and the flower, I'm not saying zinc will drive that 100%, but what I am suggesting is that a little bit of extra zinc can help smooth those expressions out and to really get the plants to do that a little bit better.
Oh man, do that but better with Rooted Leaf. Generation 3. Gen 3 is out, everybody. Microflow should be out by the time you're hearing this. If not, stay tuned. I got a little bottle of it in my garden. Thank you, Nick. Switched over to that this run. And go and get it, everybody. It's rootedleaf.com. It's code GrowCast for 20% off. Nick, before we wrap this up, man, this has been a powerhouse of an episode. It's a lot to chew on here, but you dropped some really good stuff. Definitely going deeper, definitely going more advanced. And I picked up a lot of new, again, kind of reframing the way that I think about what's going on when my plant interacts with H2O. Really great episode, Nick. What else you got? Any sort of teasers? Any events? Or just get at rootedleaf.com, code GrowCast.
Yeah, get at it, rootedleaf.com/GrowCast. I'm in a little bit of a wormhole right now, so once I figure out where exactly I'm at, I will come back and report. I do recommend people check out the blog post. Like I said, there's a lot of what I'm trying to convey there is just our philosophy about how we look at plants. There's some really interesting things about what happens in nature outside of plant biology that it just seems like plant biology kind of built itself around to optimize this thing in nature. So a lot of the work that we're doing with Gen 3 revolves specifically around, this stuff. and plants being quantum scale particle decelerators. I try to make that case pretty strongly. And really, as we continue to move forward, I'm going to build out that metaphor a little bit more strongly. Right now, we've been looking at it just in terms of the metaphor, but in reality, that is how plants operate. They are quantum scale particle decelerators. And, the electron branch of the fork there leads towards the oxygen evolution complex, and the proton side of the branch leads towards my favorite enzyme in nature. It's called the thylakoidal carbonic anhydrase, which we can get into on one of the episodes here. We can unpack it, but I'm going to start to make the case more and more strongly over the next few months that it's not just a metaphor that plants are quantum scale particle decelerators. This is actually the case. And when we zoom in at something like the OEC, we're zooming in on such a fine scale. The structure, again, is 100,000 times thinner than the human hair. So we need to change the way that we look about this. This is why the scale dependent paradigm shift is so important. We need to be able to adopt and pick up this language of quantum electrodynamics when we're talking about something that's only 1 nanometer wide, but we need to be able to revert back to and fall on language of biochemistry when we're talking about the cytoplasm and the soup in the cell, or even the whole plant, when what happens across the whole plant. So building out that kind of paradigm shift is really important for people, and I want to try to convey that to folks more and more as we continue to go down this path of integrating quantum physics and engineering our products based on these physics equations that speak very strongly to increasing yield and quality through providing more energy for the plants and quantifying that energy. So, that's where I'm at.
This has been a deep dive, my friend. You did great this episode. Thank you so much, Nick. We always appreciate you. It's rootedleaf.com. It's code GrowCast. Get at us, everybody. Tell us how much you like this episode. Let Nick know how much you like this episode at The Rooted Leaf on Instagram. That's at The Rooted Leaf on Instagram and rootedleaf.com. One more time, thank you, Nick. Appreciate you, buddy. Thank you for always serving the GrowCast community, and I look forward to the next deep dive real soon. Thank you so much, everybody. Stay tuned. We got more GrowCast coming at you. Like I said, we're on video now, so check us out. It's growcast.com for all the things. I'll see you on the next episode. Bye-bye for now. This is Nick from Rooted Leaf and Jordan River signing off, saying be safe out there, everybody, and stick around with GrowCast so you never have to grow alone. Bye-bye, everyone. That's our show. Thank you so much for listening. Thank you to Nick from Rooted Leaf. Of course, it's rootedleaf.com, code GrowCast for 20% off. Plus, you get a free bottle of Microflow with every order for a limited time. Quick shout out to GrowCast Seed Co. GrowCast.com is where you go. There you can find the membership, the classes, and the seeds. We got $10 off our key lime truffle, key lime shuffle, and leche lima crosses. This is some pink flowers, folks. We're seeing a bunch of violet and pink and red coming out of these flowers. They're pungent, they're funky. The Key Lime Madness crosses have been popping off. Stay tuned for an episode with Rich coming out soon where he talks all about these crosses, but you can get them now. Go to growcast.com, click seeds, and check them out for a limited time. $10 off all of those great strains from the new KLM drop. All right, everybody, that's our show. Thank you so much for tuning in. I'll see you on the next one. Be safe out there and never grow alone. Bye, everybody.